right. So welcome everyone to our first live in-person MRC seminar of the semester. So welcome back for fall, or for the new students, just welcome in general. So today we have Professor Mehta, who is an associate professor of electrical and computer engineering and mechanical and aerospace engineering at UCLA. And he directs the Laboratory for Embedded Machines and Ubiquitous Robots, or LEMUR. And so, as you will be able to see more of that today. And so he has received the DARPA YFA in 2022, the NSF Career Award in 2018, and was named a Samueli Fellow. Am I saying that right? Samueli?
Samueli.
Oh man, I've seen that name so many times. I've been saying it very incorrectly. Samueli?
Yeah.
Excellent. Fellow in 2015. Also, a little bit of trivia. Overlapped, was in the same lab as the founding director of the MRC, Sarah Bergbrighter, who's now a professor at Carnegie Mellon. So let's all give him a welcome round of applause.
Thanks for the introduction. Thank you all for showing up. I didn't realize this was the kickoff talk. So great. I usually start by saying this is going to be a bit of a different talk than you normally see, but if you haven't seen any yet, then great. This will set perhaps the stage. My talk is a little different than usual academic talks in that I'm spending a lot more time in this talk talking about my motivation, which gives me a bit less time to talk about the actual research that I've done. I think the motivation is the most important part of what I do. And it's like I'm a professor, I don't actually do anything anymore. So that's the part I talk about. Since I do have less time to talk about the research, I will pretty much speed through all of it. So if you have any questions or want to talk more about anything, feel free to just interrupt me. Raise your hand, just speak up, whatever it is, and I'll stop and go into more of that, even for the motivation. So feel free to interrupt. Like this can be much more of a conversation than me just standing here and performing for all y'all. So I run the Laboratory for Embedded Machines and Ubiquitous Robots, LEMUR, and we have sort of a broad vision, and that's to get more people to be engineering capable. They don't need to be engineers, they need to make stuff, and that's really what the difference is. And so, that's sort of great as a high-level post. We are an engineering lab. We have to do engineering research. So we talk about a bunch of specific topics that span electrical, mechanical, chemical, material science, all this stuff. We talk about the brains of robots. We talk about sort of their behaviors, but we mostly talk about building them, designing them, and building them. And that's really what the focus of my talk today is going to be, this like, what does it take to design, to build, to create? I have plenty of work on the other stuff that I'm just not going to talk about, but if you want to hear more about it, feel free to contact me afterwards, stay around, throw me some questions, whatever it may be. The goal of everything that we do is to make people more able to design and engineer their own solutions for whatever their problems may be. Now, I'll sort of use the words robot and robotics interchangeably with engineering, creation, and making, not because I feel like robots are the only things worth making, but really nothing else is worth making. Robots are cool. They're fun, they are interactive, and really everything that you could make is kind of a robot. What is a robot? It has some structure, it has some functionality. Whatever you make, we'll just call it a robot, and that way I can call myself a roboticist and do whatever the heck I want. So don't be like limited into thinking about the robot as any particular kind of thing, and we'll see a whole bunch of different robots over the course of the day. But like I said, I'm going to start out with that motivation. Why are we building robots? Why are we designing robots? And in fact, why in our group are we not actually designing and building the robots ourselves? Why are we coming up with solutions that help other people build robots? And now I'm going to go into a bunch of social science research results that I did not create. I sort of cherry-picked a whole bunch of data from the world around me. And I'm also not a social scientist, so I take this information, I put my own spin on it. I'm going to make a bunch of opinion claims, and they may or may not hold water for any of you all individually. I encourage you to take a look at the data, which is numbers, and make your own inferences from them. But I'll start with a few snapshots of money. And as much as it pains me to admit, we are in a capitalist society, and so money is kind of the core of everything. And we can take a look at sort of the gap. The people who have and the people who don't have, and how far apart they are. And we can think about their income gap, like how much they make on a per time basis, or if we're engineers, we can integrate it and think about a wealth gap, how much you have aggregated overall. And the fact of the matter is those who have are having more, and those who have not are having less. And in fact, many people have less than nothing. And this is an issue. And why is this an issue? It turns out resources in a capitalist world map to money in a capitalist world maps to resources. And one very important resource is technology. And we can sort of see this gap about who has access to what, like broadband, laptops, connectivity, all that sort of stuff. And that's all well and good, but now access to technology has further follow-on consequences because that resource translates to education. We are all in a room filled with computers and monitors and stuff. There's, you have plenty of interactivity in your courses and your education, not only here but leading up to here. And we can sort of see some of these graphs. These are broken down by various demographics. The more main takeaway behind these is not so much the demographic information itself, but how that is used to correlate access to technology to access to education. And so having less access to technology translates to not having the same level of outcome from an educational program, from your schooling. And things keep going from there. If you don't have access to education, that compounds. And then, not having sufficient education now translates to the next generation having less resources. This is sort of like the map from when we had a way of doing a very careful comparative study to like the capabilities of education before pandemic to the capabilities of education during pandemic, which were drastically reduced, all else being equal. And so we can see some of these trends across time. And it keeps going, right? Like there's this idea of the pipeline, but really that translates to more education, more money, more education for the next generation. And you can sort of see, how the parents' level of resource translates to kids' level of education. And so we have this feedback loop. And it's a positive feedback loop where the word positive is, again, used in an engineering sense, where when you have a feedback loop with positive feedback, the signal rails out. We have this increasing separation between the haves and the have-nots. And that sucks. That's not great. And so I'll say, before I sort of give my take on how I may try to approach this, it gets just a little bit worse in that this problem, this mapping to educational resources, and then the feedback cycle starts early. And we can look at not only access to education, but then engagement in that education as well. And we can look at this in terms of truancy, the participation in the school process. And again, this mapping is very strongly correlated with income, with the resources, and it starts early. It sort of continues on. Lower education now translates to lower income later, and it starts early. Starts as early as kindergarten. Now, I'm not going to go ahead and say there's a very clear causal relationship between from one to the next. There's a lot of confounding factors where there's a common origin that leads to many of these together, but nonetheless, it all comes together to see this compounding loop. And so that is kind of a dire picture. And this is sort of the core of my motivation in that I look at that and say, how can I, an engineer, go ahead and start addressing some of this? There's certainly better ways of addressing, or more comprehensive ways of addressing it through policy, through economics, through outreach, and so on. But as an engineer, I can take a look at this one component of the feedback loop and say, mapping resources to educational capabilities, can I try to make education lower resource intensive? Can we think about what does it take to learn about engineering right now, learn about making, learn about creation, and make that more accessible to more people? And again, I'm using engineering and robotics as sort of a catch-all to relate to general creation, and in fact, translates down to agency. Like if you feel like you can do something, if you can make your own impact, maybe that'll give you the ideas or sort of give you the support necessary to go on and then continue on with a long and productive and happy life. This is sort of the broad principle. It's known in many terms. One of the sort of the aspects of it is this idea of the endowment effect, which is when you've created something yourself, you give it more value. You have sort of a better connection to it, and so therefore this idea of making translates into sort of having a better sense of self. And so that's how I put all this together to say that my motivation comes from there. But it turns out that that's not the only value to the research that I do. Starting from that as sort of the motivating goals for me, we also end up with some of the more traditional engineering metrics of performance and of value. And for that, I'll turn to sort of a common approach throughout engineering, this idea of trade-offs, a Pareto front. You can look at any two axes and say there's a trade-off between them. And I took this this slide from one of my colleagues' papers where they were looking at this concept of fairness. I can sort of look at it broadly as equity or access or something like that against whatever other performance metrics we have, speed or energy efficiency or power, or whatever you want to talk about in terms of your engineering performance. Oh, and I thought I had a nice animation here, but it disappeared. The idea is that as we do engineering, we push that Pareto curve out. We increase sort of the overall trade-off space. And so if we focus on increasing equity and access, then whatever developments we come up with are probably going to improve these other performance metrics as well. Another way to look at that is, I'm an avid GNU Linux user, and I look at the philosophy of Unix, which sort of kicked this all off. Is the idea is you have individual things. You have one thing, you do it well. In the world of robotics, we've seen a lot of examples of trying to do everything. And here's a video from the DARPA Robotics Challenge. It's a little bit dated now. We're coming up on a decade, but I don't think the right lessons have been learned from this, because we look at all these failures, and the takeaway is, well, we need to get better. And we see, people are certainly getting better at building these all-purpose robots. I look at this and say, why should we have a robot be able to both, open a door and drive a car at the same time? Sure, we can, but we've had millions of years of evolution to get here. Maybe we should think about having one robot do one thing and do it well. And translating this back to my idea of lower resource robots, we can take a look back at the philosophy of Unix and look at this idea that part of development, part of improvement, part of getting those performance benefits out includes failure. It includes having some of these failures so that we can learn from it and try early, try often, and fix things when you need to. Now, when you have $1 million robot that is what you're trying to get to do something, you're very hesitant to have it fall over in case you ruin your $1 million investment. But let's say we develop $1 robots. I mean, yeah, $1 is still kind of quite a lot for a large portion of the world's population, but it's a lot less than $1 million. And now you can try all sorts of random things, and you can fail. And if it doesn't work, you can scrap it, learn from it, and try again. So there's a lot of benefits, this idea of lowering the resource investment needed for engineering education. And so, that's sort of the approach that I bring to this, where if we're thinking about getting more people to build stuff, we really need to think about the creation process. And rather than think about it in terms of us, the expert engineers, we want to think about the non-expert user, maybe somebody who has limitations on what they can bring to the table. But we want to give them the same process that we have for engineering. Start with some idea and translate that idea into some intuition of how a solution should work. From there, go ahead and actually manufacture it, build it, turn it into a physical realization. Test it out, see how it works. Make sure it has behaviors associated with it, and have it try to execute the solution. And learn from that. Whatever happens, you have generated some new insight. Go again. Figure out what you need to change, build a new system, and end up with your own custom creations, your own solutions. And ultimately, we want to put all this together, say, I'm talking to a crew of people from MRC, but ultimately, we want to be talking to everybody. Whoever wants to create, whoever wants to build, whoever wants to design and make should have all the tools available, all the knowledge and all the capabilities to go ahead and do it for themselves. So I think this is a good time to take a pause. That was sort of my motivation. That was why I'm here, why I'm doing everything. Are there any questions, anything that people want to discuss more, or we can jump into the research? So let's go ahead, and then we can sort of see how this plays out. But before I talk about the research, I want to make it clear, like I said before, I am a professor now. I don't actually do anything. These are the people that actually did all the work that I'm going to show. I have a bunch of grad students and undergrads and plenty of people who have contributed to all of this. I'm just a pretty face that talks about it. I've also had a bunch of collaborators, people from other universities and so on. So I'm not trying to take credit for their work, I'm just trying to take credit for their work. So let's start with sort of like where I see this going. Like, how does this all connect back? You'll see this as a theme throughout my talk. I'll give the punchline first and then sort of build up to it again. This idea of having more people make, having more makers that don't have necessarily the same backgrounds. And so I'll start with an example. These are examples. These are images and videos and things taken from the final presentation of a student that I had for an 8-week-long internship. This was a student who was a first-year undergrad at a community college nearby, first-generation student in college, not an engineer yet at this time, and created a bunch of these tools, created these robots that you see, created the behaviors that these robots are executing. These are things that are fairly well developed, especially for somebody who's 8 weeks away from just seeing creation for the first time. This is really what I want to get to. How did this happen? Like, I started by, I have this this paper-based robot that I designed during my postdoc life, and it's very cheap. It's, I think, $10 worth of materials, of which $8 of those are the batteries. You cut it out of paper, you fold it up, you have this 2-wheeled vehicle. I give my students, my summer interns, this toy to start with, along with the information for how to design it and how to build it and use it, and tell them to go do something else. Start from there and do something else interesting with it. And these are a bunch of other projects that have come out of this 8-week internship. You can take these, instead of just a 2-wheeled car, you can make a 4-wheeled car with steering, different kinds of steering. You can put it on a floating platform and have it like become a steerable boat, put it in the air, make a blimp. That middle thing should have been a blimp. Is that? Oh, okay, great. And so, like, there's this approach for starting with something, but also giving students the ability, or giving people the ability to then create something of their own from there. So that's sort of where I'm going with this, and I'll go ahead and start going through the steps that we've been doing in our lab to make that pipeline a little bit more accessible. So maybe you don't have to go to a research institution for 8 weeks to make that happen. You can just stay at home, and with whatever you have at home, still become that kind of roboticist. So I'll start from this idea of like the steps of the creation process, and start at this manufacturing step. Like, we want people to be able to build their ideas, build their creations. And so like this idea of user-driven manufacturing, that's the term printability. And this is sort of the start of my printable robot life as a postdoc. I built this vehicle where the body was this rapid manufacturing process where you cut and fold paper. That's what I called printable at that time. Like, we made the body, and that was huge, because up until now you needed either a machine shop or maybe a 3D printer, but you needed like some kind of infrastructure and some like established manufacturing pipeline. Now you can do it with paper and scissors. And so that's the idea of printability. That's where it started. But it turns out a robot is much more than just a body. There's a lot of other stuff going on. In order to be a robot, you probably need some sensing, some actuation, some intelligence. There's a lot of these other components that are necessary. There's also power. And I'll say, throughout this entire talk, in fact, most of our research world, we haven't really focused on the question of power. Not because it's not important, but mostly because that's a very hard problem that I don't have the background to do. But I think it's very important, and right now we have collaborations for that. But if anyone has solutions or can come up with solutions, great. Let's fill out this whole story. But really thinking about just sort of the brains, the intelligence, the rest of the system beyond the body, that wasn't really printable. It wasn't really rapidly manufacturable. I have to go and buy electronics, motors, and the microcontrollers and so on. Certainly getting a lot cheaper, but still not easily accessible. They're cheap, but you need to live somewhere on an Amazon delivery route to be able to get it, or you need to have some way of interacting with sort of the broader commerce world. And so, sort of drawing a parallel to like the first idea was, let's start with some smart or some capable material. This idea of paper, which I'll use paper interchangeably with sort of a broad general 2D substrate. Sometimes they're plastic sheets, sometimes they're fiber. Maybe we can use wood sheets. But you have this idea of a 2D material that has a lot of interesting mechanical properties, where if you design it in the right way, in our case using cut and fold processes, you cut it and fold it kind of like origami or kirigami, you end up with the ability to customize a a solution in the real world, a 3D solution. You can quickly and cheaply manufacture things with the right mechanical properties or sort of interactive dynamic properties and so on. That was the ability that we created with the idea of printable bodies. Well, if we want to now extend that to the rest of the robotic system, we can think about having some more still accessible materials in addition to paper. Now we're using nylon string. In this case, we're using silver-coated nylon string, so conductive sewing thread, fairly easily accessible. If you don't have that, you can take regular nylon thread and find some other way of heating it up. And now we have, again, through careful design, mechanism design, we have the ability to create these fully printable robots. The idea that using just paper and string now and off-the-shelf manufacturing things like scissors and tape and tying knots and whatever you have to be able to potentially create these fully printable robots. The idea is, this sort of a schematic drawing where everything can be made out of these common or at least more accessible materials with common or at least more accessible manufacturing tools if you can fill in that black bar in the middle. Whatever that design and manufacturing process is, to be able to realize your intelligent, programmable robots. And so, punchline first, here's a robot built entirely out of string and paper with wires coming in from off the screen that's sending power in from a lab power source. So again, power is not a part of this, but it's paper and string, and when you put power in, it starts swimming. It's got a little flapper and it moves along. Maybe not necessarily intelligent, but it's still a robot. It has active response to the environment. Here's another example that it's same general principle. It's not entirely paper and string. Now we put little aluminum foil weights to give it a little bit more motion. You can sort of see it skittering along on the ground. Power coming in off board, but the rest of it is printable, and you have this robot driving around. Yes?
What's the actuation mechanism?
So I'll get into that right now. Let me explain the actuation mechanism. This is the core feature of its design, of both of those designs. It's an oscillator that moves some mechanical element back and forth. In this case, the mechanical element, in the case of the walking robot, the mechanical element was this off-center, this like heavy mass that kind of pushed it forward. The swimming one had a little flapper. Those are driven by this the bistable beam in the center. It's a mechanically nonlinear element that causes rapid shift from one mechanical state to another. They're driven by what we're calling here this conductive supercoiled polymer actuator. This is the nylon thread. Nylon thread, when it heats up, expands. But it turns out if you have a coil of this material that's sort of coiled really tightly, when the material expands because of the contact forces in the coils, the entire coiled string contracts. It's like a muscle. We didn't come up with this. This is work from a couple other groups, UT Dallas and UC San Diego, have sort of developed this actuator. But fundamentally, you heat it up somehow. In this case, we put a current across it and it heats up, and then it contracts. And so we now encase this particular actuator in this mechanism with this nonlinear mechanical element to get the driver behind these robots. Just to point out, like, it's really low cost. It's folded paper and nylon string. I don't know how we got to 40 cents. That seems really high for a scrap of paper. But I think there was there were some like scaling things that we were trying to say. If all you built was this robot and you bought just enough for all this, well, if you start economies of scaling up, you'll get even lower. But you can't get, like, the highest that we've come to with this is 40 cents. It took some time. It does require user activity, not a whole lot of time. This was, I'll say 1.5 hours is the second time you build it. The first time it'll probably take you many hours more, but once you've done it once or twice, then it's doable. And it really is not, it's not a high power system. It's something that you can, we ran it from a lab power supply, so we could do the measurements, but you could probably run this from a solar cell. Now we haven't run it from a solar cell, so I don't want to make that claim, but there's many ways you can do it. Maybe stick some pennies in a lemon and see if you can drive this thing. But we're getting this idea of accessibility. Like, this is something that is within bounds, within realm of a lot more people than many sort of conventional educational robots. Just very quickly how it works. We have these two muscles that are acting in opposition to each other. When one is actuated, it's pulling. With that nonlinear element, It keeps pulling until it's gotten enough force to snap all the way through. And when it snaps through, it switches the actuation into the other muscle. But because it's already snapped it has that nonlinearity, it snaps all the way through. Now the other muscle is active, and it's pulling it back the other way until it snaps through, and now we have this repeated motion. It turns out we don't have to connect it in such a way that it just oscillates back and forth. If we take that particular core nonlinearity and extract all of the possible electrical connections from this device, we end up with a multiplexer. This is sort of an electronic device that is common through the electronics world. If you build FPGAs, or if you build designs in FPGAs, field programmable gate arrays, you may be using a lot of these as sort of the core building block because it is a fundamental logic device. It's a universal logic device. You can build any logic gate with this device. It behaves, I'm going to zip through a lot of these in the interest of getting through more material. It behaves very much like a regular logic device. We can do all the characterization for noise performance and noise rejection. We can build logic gates out of this. We can have an inverter or simple and OR gates, NAND NORs, cascade them. So this is sort of like the big old truth table of all of your common electronic gates. We can cascade them to build more complex logic gates. Because it's a universal system, we go on beyond logic. We can build devices like a counter and start counting in binary up to 16 or whatever we want to do. We can take this thing, and because it is a mechanical element in there, we can, when we remove power, it stays exactly where it is. And now we have memory. We can use this as a bit and build arrays of memories and start now creating our computer or computational elements for these things, all with paper and string. In some sense, this is going back to the initial era of computers. The first computers were fully mechanical devices with gears and cogs and stuff. Now we're building it out of paper and string. And why are we going to do all that? Because the robots that I showed you before, they weren't really intelligent. They didn't really have responsivity. They did one thing, and they did it well. They swam or walked. But we want some programmability. We want them to respond to their environment. And so here's an example of a possible robot or a device that responds very simply to its environment, inspired by Venus flytrap. Venus flytraps are plants that eat animals, eat bugs, but it takes a lot of energy to close and open. And so it doesn't want to close its jaws unless it's actually an animal inside or an insect inside that will give it the nutrition. So it has sensors along the inside that will only respond if there's an active insect in it. It has multiple sensors, and they all have to be triggered in a row with some time sequence, so that it says, all right, this is something alive, not just a leaf that fell into my trap. And so we can think about this in terms of behavior and say, let's put a couple sensors, 2 sensors on here, and only when they both get triggered will we consider that it's something worth eating, and that's when we'll actuate our actuators and close up. And here we'll have a video that we can put together and say, with just one single sensor triggered, nah, not going to close. If we trigger both of them, then this thing will close up. Now, this is a device. This robot is built, again, entirely out of paper and string. It's sitting on a base that we just glued down to make it stay where it is. But there's paper and string and power coming off board, and now we have this sort of intelligent behavior. Super cheap, super accessible. You can build it with scissors and some random stuff that you have lying around. But going back to some just characteristics of behavior, going back to this concept of growing the Pareto curve, it turns out this robot actually has some advantages over conventional robots. Now, you're never going to run computer vision on this thing. It's not that kind of advantage. But it does have advantages in terms of its robustness to various environmental factors. Where if you wanted to put a robot inside an MRI, magnetic resonance imaging machine, you can't. You can't have any conventional electronics, you can't have any conventional metal parts, but you can have paper and string. And this robot works just the same in an MRI as it does on your desktop. One of the conventional tests or demonstrations of soft robotics is this idea of mechanical deformation. You can step on this thing. And yeah, there'll be a few creases on it, may not fold quite as well, but it'll still open and close. If you try stepping on your phone, probably not going to work quite as well after that. And so on. There's sort of a lot of this robustness built into this idea of low-cost materials. we can build like a variety of other robots with this concept. In this case, we can sort of demonstrate some more logic, but it's not limited to its own ecosystem. You're not only allowed to build robots out of paper and string. You can, if you have motors and you want to use motors, throw some motors in there, and we can get robots where in this case the intelligence is still captured in the paper and string structures on top, but that intelligence is now driving regular motors that go and move legs around and so on. You can still have sensors that are sensing the environment through these contact switches. We can talk about the memory aspect of these. And here's an example of where we built a 4-word memory bank with 2 bits per word. So not a whole lot of memory, but enough to be able to have a vehicle that we can reprogram on the fly. Back when I was a grad student, we called this method of programming GSWT, graduate student with tweezers. You go in and you set the memory by twiddling little pieces of paper, and you can have this vehicle programmed to operate on any number of, any 8 different trajectories. And we picked the trajectories accordingly to match our home, but you can design a system with sort of mechanically respond however you would like it to behave. Okay. So in this case, for all these example robots, we sort of focused on sort of the conventional robot design process, where you have a body, you have a brains, and you have the brains driving the body through some interactions and through some kind of program behavior using electronic circuits. But it turns out if we're talking about building things where we have the control over the building, when we can build stuff out of our materials, then we can think about a different paradigm where the materials themselves have the behavior programmed into it. We're calling this mechanical intelligence, but there's a lot of sort of ways of describing it. The idea is that we want to be able to create this now metamaterial, the metamaterial that is programmable. In this case, we're trying to consider the programmability in terms of its mechanical structure and its mechanical properties, stiffness and strength and damping ratios. And you can say by actuating it or by finding some way of driving it, you can change its mechanical properties so that the material itself can now behave differently. And maybe we can show ways of turning that into a robot. Just as a point, you may have seen this kind of idea with a push button. It's a toy that you can buy that's been around for probably a couple hundred years that uses the same principle, the principle of particle jamming. And in this case, you have a bunch of beads, and you can shape the beads in such a way that they nest, they interlock with each other, so that you thread along all these beads along a string, and by changing the tension of the string, by pulling on the string, you change the behavior of that beam, that collection of beads. You can change its stiffness, you can change its other mechanical properties. And you can actuate this conventionally. You can say, let's put a motor on it and use the motor to wind up a spool, and that pulls the string, and so you can have some super floppy bar to something that has some rigidity. You can try some of the other things. So like that same actuator that we had used in the paper robots, this nylon thread, it's a muscle. You can use that to pull the string tight, and you can actuate it with electronics. The nice thing about it, it's a thermal actuator, so you can actuate it without electronics. You just put it in some hot, in this case, a hot water bath, and it'll actuate. And so now you can maybe think about having the actuation directly driven by sensing from the environment. And the nice thing about this is it's programmable through the tension in the string. And here you can see, like, we have a block of matter. Let me start that again. You have the block of matter. You can change how stiff it is. Does the ball bounce off it, or does it get caught into it? Now that's sort of an interesting, like academically interesting case where you have the stiffness in a block, but that's not necessarily like that's enough to get us a paper out of a very prestigious journal, but it's not really that worthwhile. What we can do is turn it into a robot. Now the interesting thing about this robot, it's a robot. It walks. Very simple robots that we're building because we're sort of exploring the space. But the neat thing about this robot is it's a single degree of freedom actuation. The actuation is changing its stiffness. There's no actuators that are like moving legs or anything like that. It's just going from a super floppy robot to a super stiff robot, a mechanical structure, and we can use that to walk. Same general idea behind most soft robots. It's very robust. You squash it, you twist it, you like crumple it up and all that, and it still keeps walking. Now, why do I say this is intelligent? This is, maybe intelligence is a little bit strong, but because you're controlling this thing with its stiffness, it doesn't need to actually know about its environment. It conforms to its environment. And so you can go through tunnels and under bridges, and it doesn't really, it doesn't need to do anything. It's just we make sure that it's soft enough to get through these things. And then as it changes between soft and hard, it walks along. So these are some of the recent results. And these I guess this is sort of another element of building low-cost robots using string, and in this case beads, so not necessarily made out of paper, although we could. I don't know. I've not tried it. But using, again, simple materials, simple designs, simple processes to come up with interesting behaviors. Now, I say using these things to create. There's a big gap in there. That word using is doing a lot of heavy lifting in that statement. You need to know how to use these to do it. And right now, all of those robots and designs that I showed were built by my graduate students. They were built by people who have had a lot of years of education at prestigious universities, getting the kind of background needed to be an engineer today. We'd like to make that not as onerous. And so now I'll get into the next collection of stuff that we've done, this idea of computational design. Taking the knowledge that we have developed as engineers going through school, wrapping that up so that other people who are not engineers, who have not gone through the same schooling, can still use all of that to do this kind of creation. This is the design phase of the creation cycle. Now, the reason this is challenging is because when we talk about robots, we have a lot of intersecting domains: mechanics, electronics, thermal, optical, who knows what other parts go into all of this. And if we wanted to figure out how these things work for real, we have to use complicated, sophisticated numerical analysis programs where just figuring out how to run the program, maybe even how to install the program, means you probably have to be in a PhD program somewhere. And then you get results, and you definitely need to be in a PhD program to understand what those results even mean. That's hard. On the other hand, you don't necessarily need to do that numerical analysis. You could use simple models. Use F equals MA, which I guess nowadays is starting to be learned in high schools or maybe even middle schools. You can use very simple analysis, and it'll give you results that you can figure out, but they don't really mean much because they're very low-order approximations, and you need to try to infer what limitations those simple results may have. So we have this sort of broad question, which is like, what do we do? How do we bridge this gap and make it so that we can understand how these systems are going to behave? When I say we, it shouldn't be us. It should be people who are not in this room today. And so we can sort of use as a sort of a surrogate case the printable oscillator, the paper and string core behind the swimming and sketching robots, and say, well, what at our core we have this actuator, this coiled muscle, and a nonlinear element, which is this bistable beam, and we want to see how it interacts. The actuator heats up, generates a force, pulls the beam, it needs to flip through, and we have this cycle. It'll give us some period. The functionality that we prescribe, the thing that we need, we say we want a robot that swims and it should be flapping 4 times a second, or we want a robot that walks and takes 10 steps every second. There's a period. Like an oscillator is pretty much governed by one parameter. So the design process is let's get this parameter given the geometry of our structure. Well, how would we do that today? We take some equations that just say how these things work. We're going to throw in some approximations and some physical relationships. We will figure out when we can use approximations and how we can connect these two domains into a single domain. And great, in that 3 slides and about 3 seconds, you've covered 1 PhD's worth of work to get this equation. And now you know how to get a period, an oscillator with a given period, given the geometry. Right? Not really. That's complicated, and I don't expect anybody to understand what's happening in this equation. I don't understand what's happening in this equation. But the nice thing about this equation is it is an equation. It is a very low order, relatively speaking, equation that has a relationship that we can now throw into a computer. It's a constraint optimization problem, which numerical solvers in MATLAB or Python or in a number of other free and open source products can just solve instantly. And so we can formulate all this. And now that this has been formulated, we don't need us anymore. I don't need to be there and my student doesn't need to be there to figure out how to do this, you throw it into a computer. And the computer will say, you need to have a muscle that is 12 centimeters long. Now, that's the muscle part of it, but it turns out the robot, remember our high-level schematic, has more than just the muscle. There's a body, there's sensors, there's actuators, and we can take all of that put together and do that same kind of modeling. Take each subsystem, figure out its constituent relations, it's the math and physics that goes into all of this, figure out how they relate to each other, and throw that into one big mixing pot. We can have things that are not just geometry, but discrete choices, like do you want a different set of actuators? We use actuators that are made out of nylon because they're cheap and disposable. But if you wanted to, or if you had access to things that are made out of carbon fiber, you can get ones that are much stronger. We use paper, again, cheap and disposable. You can cut it with scissors. Maybe you have some other materials lying around. You have some plastic sheets or whatever else. You can throw in some discrete decisions there. And put all of that into one big giant mess through that design framework, and come up with some analysis tools. And you're sort of like a snapshot of a graphical front end. Very, very. I'll say right now we're not so much into the user interface development phase just yet. So you still need to kind of know what you're doing, but you move sliders around and you see how does that change its behavior. And you can play around with it and say, all right, here's a behavioral point that I like. This is the kind of design that I want. How does this robot translate into motion? We'll give it an impulse and see, does it roll around? This idea of using the snap through instead of having a little flipper, push it on water. We have it drive a plunger that causes the cylinder to roll over. We say, hey, look, it works. After playing with the numbers, we get it to start rolling over. We can generate a manufacturing design for it. We can go ahead and build it. Realize, oh, hey, it doesn't actually work. When we hit it with one, it goes maybe almost halfway, but then it rolls back. Maybe that's because we didn't cut it quite so well because it's been a long time since I've been in kindergarten using scissors. Or maybe it's because, I'm not an engineer anymore. I teach and I don't do anything useful. But now we say, all right, well, maybe if I had two, one on each side, I push it a little bit halfway, and I use another one to push it again. And we can try this one, throw it back into the mix, do some more analysis, right? We get that iteration part of it. Very low cost. Everything is, cents worth of material and so on. Doesn't work, recycle it, try again. So that's the design process, and I sort of demonstrated that on this paper and string robot, but we're not actually limited to paper and string robots. That's certainly very very interesting to me because now we're sort of closing the loop on that design pipeline in terms of low cost. But if you have a traditional robot where you build a body out of plastic or wood or metal with conventional subtractive manufacturing materials, or maybe additive, you throw in a 3D printer there. You have a brain that's built on a circuit board where you get discrete components and solder it in, or get modules that are integrated circuits and program that whole thing. You run code on it, and you have sensors that are transducers that you buy from DigiKey and solder them on and have it drive around and do stuff. Well, you can throw this kind of integrated process onto it as well, and you have these pipelines that used to be very separate, where you have an electrical engineer figure out what controls you need, and then a computer scientist program those controls, and they're all put on a body that a mechanical engineering designed, and you turn it on and nothing works because nobody talked to each other, and so now you have to go back to the design loop and say, all right, well, turns out you need more horsepower to run this computing algorithm. But that means now you need a stronger leg to hold up the extra weight of the battery that it takes, and all this stuff. We can wrap that up into a single design process where you feed in a set of goals, a set of behavioral objectives, and it will farm it out to a bunch of different tools that we've created over the years in our lab. And I just realized when I was putting together these slides a couple days ago that we didn't actually name this integrated tool, so we should probably come up with a good name for that. But it parcels together circuit design and mechanical body design and some amount of control system design, and loops that all up and gives you this sort of design tool in the middle that doesn't require an engineer at the beginning. Okay, so in the last couple minutes before I leave some time for questions, I sort of gave snapshots of where we are, and I've sort of been hinting along the way as to where I want this research to go and where I think the important next questions are. But sort of broadly speaking, we can take this all the way back to my motivation and say, what is it that is making it hard to be an engineer today? What is making it hard to create? And I've sort of pulled out 3 points that I think are relevant, but of course there's many. And you all may have your own experiences that got you to where you are today, your own connections to people who are not in this room right now, and you may have some thoughts here. But we started with sort of the low cost. We're capitalists. We need to have money. Can we get the materials, the stuff that we build it out of, to be cheaper? But there's also access to infrastructure. A 3D printer may be able to make things out of a few dollars of the plastic, but the printer needs consistent electricity, and it needs access to repairs and materials that can be delivered by Amazon. So there's another layer on top of just the cost, but the connectivity to the sort of global economy. And then there's this big gap of knowledge of what does it take to be able to use all of these things to get to where you are. And so I sort of gave this framework of using all the low cost materials in sort of an integrated process. But that processing, we in theory can do this with just scissors and tape and knots. Mostly what all the robots that we built are built using higher grade engineering manufacturing tools. And part of that is because fundamentally they are a little bit finicky. We need some amount of precision in their manufacturing. It would be great to think about how we can design systems not just robust to being stepped on, but robust to manufacturing variations. So that when you do make this with scissors, or maybe even by just tearing paper with your hand, there's enough leeway in the design that you can go ahead and still get your desired functionality out of it. There's sort of more in the space of manufacturing infrastructure to be able to say, all right, well, given what exists with the people that we're trying to reach, not what exists in my lab today, how can that still be used in more interesting and more compelling ways to do sort of the user desired creation? We think about cost in terms of materials that we're using to build our own custom robots, but it turns out there's a lot of reusable parts or reusable information or things in the world around us. Maybe we can repurpose or leverage some of the stuff that exists in the environment. There's in this room, I'm sure there's like some integrated circuit within an arm's reach of every single person here. But even then, there's like cell phones or even feature phones have a lot of sensors in them and a lot of actuators in them. Can we use some of that? What other things exist in either the built infrastructure around us or in our own personal system? And how do we use that? How can we leverage that to do things that they're not necessarily meant for? This whole idea of expertise, I mentioned we're not really big into the user interface design yet, but we'd like to be. Thinking about this, the tools that are used right now, we have sliders that move across, and that changes numbers on a graph, and you need to figure out, does that make your robot work or not? What if we could get the user more directly involved in a more intuitive way? Perhaps using some augmented reality systems. They are coming down in cost. They're still ridiculously expensive, so that goes back to the question of infrastructure. But maybe there are some other things that we can do to more immerse the user, the creator, the designer into the world of the engineering so that there's a bigger connection to what the resulting systems are. And, I've framed it all as what it takes to get the designer, the creator, to make their final product, but we can really think about exploring that link. And we call this a middleware. It sits in between the designer and the design, and it lets you explore the consequences of various decisions that you make. You can explore it at the simple model level, through some simulation or finite analysis, into the real world, and try to bridge all those connections. Not just to make this design work, but to build your design intuition so that you can become that kind of engineer that goes ahead and designs directly. Because ultimately, where we're trying to get to is this idea of something that sits in between the designer and the design, a tutor, an engineering instructor, some system that involves all of our current aggregated knowledge and uses it to help the user create their robot that they want to create in such a way that they learn from that process, they become their own engineer, and later on, they can be their own roboticist. They can come up with the ideas, implement these ideas, and then deliver these solutions out to the world. And that's really where we're going. That's what I'd like to see happen with all the research that I do, with all the research that everyone does. Pulling all this together, that's the question. What is it going to take so that we all can do the exact same things that everyone who's not in this room can also do? So you've all been a very attentive audience. I hope I've kept your attention till now, but now let's flip the story a little bit, and I'd like to hear from you. Did I inspire something? Are there any questions? What is it that we can do together as a collection of engineers to go ahead and bring engineering to everyone else?
I do have a question about what designs you found are easiest and more robust, right? So I'm thinking the crab is potentially a little harder to build than say the walker. Do we have access to those plans? Are they on your website or something?
That's a good. I'll answer the second question. The second part first. We have them all in Git repositories somewhere. They're not aggregated on our website. We should do that. This is one of the challenges, and I'm gonna flip that on all of y'all. So blame him, not me. Be very good about documentation, because later on you're gonna be talking about something you did, and if you don't have it documented, then you're gonna have to give the super awkward response like, well, yes, in theory somebody could do it, and the whole reason we did it was so that somebody else could do it, but not quite yet because we don't have all of it aggregated together with nicely laid out plans. We should, and the hope is that we will, and then you can go ahead and cut and fold one of these things yourself. But now to the first question, some are definitely easier than others. And I'll say like that little sketching robot that goes back and forth, of all those sort of paper and string based designs, that one is the easiest to move. That's the one that moves the best. But it turns out just that oscillator itself is kind of finicky. And we've spent a lot of time figuring out why it's finicky, and this is something that you do need a PhD student to do. It has to do with sort of the interplay between the material property of the thing that we built it on and the thermal property of that actuator. So that's complicated. That's where we started going to these bead-based designs where it doesn't really matter how you pull the string, as long as you pull it, it'll do something interesting. So I'll say that tripod robot that sketched forward just by changing the tension of the string, that's the easiest one to build. All you do is you get these linear actuators, and you can do it with these nylon actuators. You can get nitinol, shape memory alloy actuators. You can just put a motor on there and pull a string back and forth. All of these things will get this thing sketching forward. It'll get it to go through tunnels and all that stuff. So, yeah. But there's definitely a range of how, and I'll say the difficulty is just how reliable do you need to be about the various dimensions. Like assembling it, they all take time. You're threading things on strings. You're like cutting and folding and putting things together. It's not challenging, but it is time consuming.
Other questions for everyone? Cool. All right, well, I'm going to come up. We have a couple of presents for you for coming out here in order of importance.
Ooh.
So we've got
turtle.
This cool looking terrapin turtles. That's our mascot of our university.
Thank you.
We've also gotten you this mug, and then most importantly, paper.
Excellent.
Because I think we've all learned what can
Power
be
of
done
paper.
with paper. I'm just kidding. You should use this to hold those.
Awesome.
But thank you
Great.
so much for coming.
And thank you all. I'm glad to have had this opportunity to talk to you.
All right. So I know we're a little bit close to that 3 p.m. mark. I know some people have to run to their next class. But if you have some time or you want to ask some questions directly to our speaker, feel free to stay. We've got cookies.
My email address is up there, so feel free to send me an email as well with anything any questions you may have.
Awesome. All right. Thank you, and see you all soon.